Welcome to Chapter 5. Remember I said Chapter 4 got pretty theoretical, and it did. This gets much more computational. So if you've taken Calc 3 before, or you've done work with vectors and dot products and things, some of this may seem very much familiar, and that's good, but let's go through it all because it's important. Vectors in R2 exist on the xy plane. So our goal here is to extend this to Rn. So we're going to try to extend vectors to Rn. So n tuples. X sub 1, X sub 2, all the way till you get to X sub n. So you could be an R43, the set of all 43 tuples. What are the rules? Well, a lot of the rules are the same. They just extend to an extra dimension. So suppose you've got you want the magnitude of the vector. Magnitude, also sometimes called the norm of the vector, is just, and by the way, magnitude in this textbook is written like that. You can also write it with a single bar, right? You could write it like that, and I'll understand that that's magnitude, is just going to be the square root of the first component squared plus the second component squared, all the way till I get to the nth component squared. So the first plus the second plus the third, and so forth. What that means is that the magnitude of the vector has to be greater than or equal to 0. Yes, you can have a vector of length 0, but you can't have a vector that has a negative length, right? Vectors have magnitude and direction, so if you want the vector to go the other way, it wouldn't have a negative length, it would just have a direction that goes that way. What are the standard vectors, right? The standard unit vectors, we have them for R2 and R3. So standard unit vectors work in R2 and R3. In R2, our standard unit vectors are I and j. They are the vectors 1, 0 and 0, 1. In R3, we've got 3. We've got I, j, and then that third vector that comes out of the plane. So we've got 1, 0, 0. We got 0, 1, 0. And we got 0, 0, 1. So those are the standard unit vectors. If you take a vector and multiply it by a scalar, right? So let's say C is some scalar. If you take the magnitude of a scalar times a vector, you can actually pull the scalar on the outside, right? Absolute value of the scalar times the magnitude of the vector. So this thing over here, I'm not saying find the length of the scalar. I know what the scalar is. I'm saying take the absolute value. So if you want the magnitude of -5 times a vector, you can pull the 5 on the outside, but you got to pull it out as a 5. You can't pull it out as a -5. All right, what is a unit vector? A unit vector is a vector that is 1 unit long. So a unit vector is 1 unit long, and the whole goal of a unit vector is to give the direction of the vector. So if you want to compare direction between multiple vectors, if you reduce them all to a unit vector, then you'll be able to tell if there's a difference between the direction or if they're just all going in the same direction but a different length. So suppose I've got some vector v. The unit vector would be the vector divided by its magnitude. So, for example, let's find a unit vector for the vector 3, 4. So find a unit vector for the vector v equals 3, 4. Well, the first thing I need to do in order to find the unit vector is I need to find the magnitude of the vector. So let's find the magnitude of vector v. Well, it really does come from the Pythagorean theorem. Square root of 3 squared plus 4 squared, which is going to be the square root of 9 plus 16 is 25, is 5. So the magnitude of the vector is 25. Now we should take each of those components in the vector and divide it by 5. So take the 3 and divide it by 5. Take the 4 and divide it by 5. And that's my unit vector. So this is a vector that's 1 unit long and gives me the direction in which that original vector is pointing. Sometimes a unit vector is used in calculations because we specifically want something that's 1 unit long. All right, the sum of two vectors. How do I find the sum of two vectors? You add components. Same thing works for subtraction. So I want the sum of two vectors. Suppose I've got vector 1. I'll call that u. and it has components u1, u2, all the way to u sub n, and vector v has components v1, v2, all the way to v sub n, then the sum of vector u plus vector v is just the sum component by component. So the first component is u1 plus v1, the second component is u2 plus v2, and then all the way till I get to the last one. Which means that I can only add two vectors that have the same number of components, right? It wouldn't make sense to add two vectors that are in different dimensions because you'll run out of components. Right? What if you want the distance between two vectors? Right, so suppose I've got two vectors. And on my plane, I'm going to put a vector u over here. And vector u has components u1, u2. And then vector v over here has components v1, v2. What I want to find is I want to find the distance between those two vectors. How far is it between the end of this one and the end of that one? Well, the distance formula is going to work like this. It's going to be the square root of u1 minus v1 squared plus u2 minus v2 squared. So it's going to be the difference of the components, square them, add them together. All right, there are different notations that you can use for this. You can say I want the distance between vector u and vector v, or you can say I want the distance between vector u and vector v like that. The distance has to be greater than or equal to 0. Now, when is the distance equal to 0? So when is the distance between u and v equal to 0? Well, that happens only if the two vectors are the same. Only if vector u is equal to vector v. Okay? The other thing that comes out of this is it doesn't matter what order I do it in. So the distance between vector u and vector v is the same as the distance between vector v and vector u. Right? So order doesn't matter. Okay, that's how I find the distance. How about a dot product? Okay, a dot product is a scalar. So what are we up to? Number 7 now? So for a dot product is not a vector. A dot product is a scalar. In R2, suppose I've got vector u with coordinates u1, u2, and I got vector v with coordinates v1, v2. Then the dot product of u and v, which I write as u with a big dot in the middle so I don't mistake it for a multiplication sign, is just going to be the two components that are in the first spot multiplied together, so u1, v1, and then the second components multiplied together, u2, v2, and then add them together. Now you can extend this in Rn, right? You'll end up with what? You'll end up with u1, v1 plus u2, v2 plus u3, v3 until you run out of components. So again, just like the other ones, we're only talking about doing dot products in terms of vectors that are in the same dimension. In other words, you can't do a dot product of a vector in R2 with a vector in R4. Speak of R4, let's try an example in R4. So suppose vector u is the vector 3, 7, 4, negative 2. And vector v is the vector 6, 1, negative 2, 4. I would like to find the dot product u dot v. So what do? I take 3 times 6 plus 7 times 1 plus 4 times negative 2 plus negative 2 times 4. So 3 times 6 is 18, 7 times 1 is 7, minus 8 again. That gives me a negative 16. Negative 16 plus 18 is 2. 2 plus 7 is 9. So I don't end up with a vector. I end up with a scalar. U dot v is equal to 9. All right, what is this dot product going to be used for? One of the things that the dot product can be used for is to find the angle between two vectors. And I won't go through the whole thing here, but the formula for the angle between two vectors actually comes from the law of cosines. So suppose you've got a vector u over here, right? I'll try to make the drawing the same as the last one, and vector v over here, and you want to find the angle between the two vectors. You've got a third side over here that is the distance between u and v. Remember the law of cosines, that a squared plus b squared minus 2ab cosine theta equals that third side squared? You can actually work out that formula that way, do a whole bunch of substitutions, and what you're going to come up with is this second formula that involves a dot product. So the cosine of theta equals u dot v, that scalar dot product, over the magnitude of u times the magnitude of v, which means that you can actually rewrite this in two other formulas. One of them is if you multiply both sides by the denominator, you get the magnitude of u times the magnitude of v times the cosine of the angle between them is the dot product, right? So there's a way to write the dot product as a function of the magnitude of the vectors and the cosine of the angle between them. The other thing is if you want the angle is the inverse cosine of u dot v over magnitude u, magnitude v. So, and again, this thing is the dot product. I'm not trying to multiply those two vectors together. All right, let's take a look at an example then. Suppose I've got two vectors and I want to find the angle between the two vectors. So I'd like to find the angle between the vectors 6, 4 and 7, negative 2. So I've got to find a bunch of things. You can do it all at once. I'm going to try to list my information on the side here separately. And then I'll pull them all together at the end. So the magnitude of vector u is going to be 6 squared plus 4 squared. So 4 squared is 16. 16 plus 36 is the square root of 52. All right, the magnitude of vector v is going to be the square root of 49 plus 4, right? 7 squared and then negative 2 squared is a positive. So that gives me the square root of 53. The other thing that I need is I need the dot product. So I need u dot v as 6 times 7 plus 4 times negative 2. Well, 42 minus 8 is 34. All right, so the cosine of theta is equal to u dot v, which is 34, over magnitude of u, magnitude of v. Once you do that, then the hard part is entering it correctly. So you can get a decimal approximation for that and then do the inverse cosine. All right, so theta is going to be the inverse cosine of that, and then just check to see what mode you're in. I'm going to answer my question in degrees. So when I threw this on my calculator, I got 49.64 degrees. Is that a reasonable answer? Well, let's see. The vector 6, 4 goes 6 to the right and 4 up. So maybe that's vector u. Vector v goes 7 to the right and 2 down. 49-degree angle is a reasonable angle between those two vectors. And you notice that it doesn't matter that it crossed the x-axis partway between. That wasn't one of the things we were worried about. All right, a couple of things come out of this. One is, if you go into the formula that we just used for cosine, that cosine of theta equals the dot product of u and v over the magnitude of u, magnitude of v, the cosine can't be any bigger than 1. Cosine can't be any bigger than 1. Which means what? Which means that the numerator can't be any bigger than the denominator. So the numerator can be equal to the denominator, but the numerator can't be more than the denominator. So the numerator has to be less than or equal to the denominator. Otherwise, we don't have a valid value for cosine. And that's actually a theorem. It's called the Cauchy-Schwarz inequality. And I think there's a problem I put on one of your labs to take a look at this, the Cauchy-Schwarz inequality. And that is that the numerator, absolute value of the dot product, because dot products can be negative, has to be less than or equal to the magnitude of u times the magnitude of v. And that's for vectors in Rn. And again, that first thing is the absolute value of the dot product. And where does it all come from? It comes from the fact that I can't have a numerator that's greater than a denominator if it's equal to cosine. A couple of things about dot products that are kind of interesting. You can look through the whole list of properties of dot products in the textbook, but there's a couple that I want to highlight. So some properties of dot products. Doesn't matter what order you do them in. You can distribute amongst 3 dot products. So if you have a dot product of u and v plus w, then when you distribute that first vector, right, this is a dot product, you're going to end up with the dot product of u and v plus the dot product of u and w. So same thing as distributing over multiplication. You just have to realize that the operation is no longer multiplication. The operation is dot product. On the other hand, if you have a scalar times a dot product, so a scalar times a dot product of u and v, the way it works is as a scalar times one of those two, a scalar times u dot v, or you can do it as u dot the scalar times v. But you realize that the scalar only applies to one and not both. Right, another property that's going to come out of this is what happens if you try to do the dot product of a vector on itself. Well, when you do the dot product of a vector on itself, really what you've done is you've found the magnitude of the vector squared. Because throw that back into the formula for magnitude, and the dot product of a vector on itself is going to be v1, v1 plus v2, v2 plus v3, v3. So you're going to end up with the magnitude of the vector squared. So for example, suppose I've got this vector 4, 2, and I want to find the magnitude of the vector squared. And I want to find the magnitude of the vector squared. I could do the dot product of 4, 2 dot 4, 2. 4 times 4 is 16. 2 times 2 is 4. That'll give me 20. I could also then take the square root of the vector times the vector, and that's actually another way to find the magnitude of the vector. So if I wanted to find the magnitude of this vector, once I had the dot product of the vector in itself, then take the square root, and that's the magnitude of that vector. And you can try it, right? A squared plus b squared, 16 plus 4 is 20. Take the square root, and that's the magnitude of my vector. Here's another property for these dot products and vectors. Suppose I had go back to my cosine example. So I'm going to call these orthogonal vectors. When is the cosine of theta equals 0? The cosine of theta equals 0 at the top of the unit circle. That happens when theta is equal to pi over 2. So what if I went back to my formula and I replaced the cosine of theta with a 0? So what if 0 equals u dot v over magnitude u, magnitude v? Well, the only way that can happen is if the dot product is 0. Happens if u dot v is equal to 0, meaning that I can figure out whether two vectors are perpendicular by looking at their dot product. So two vectors are perpendicular. We use orthogonal generally for cases outside of R2 or R3 because once you're into like R4 and R5, there's no physical representation of that. So the vectors are perpendicular or orthogonal if the dot product is 0. And that's a real quick way to see whether vectors are orthogonal. So suppose I have these two vectors. I've got vector u as the vector 1, negative 2, 3, and I've got vector w as 3, 6, 3. Take their dot product. Find u dot w, and I get 1 times 3 is 3, negative 2 times 6 is negative 12, 3 times 3 is 9, that is 0, so yes, these two vectors are orthogonal. All right, this next theorem goes with something that you probably learned in high school geometry, but this is taking it one step further, and that is the triangle inequality. Remember, if you have three lengths and you're trying to figure out whether or not those three lengths make a triangle, the sum of any two sides has to be bigger than the third. So if you've got a triangle that looks like this, here's side A, here's side B, here's side C, if you add A and B together and they're not bigger than C, then you don't have a triangle, because what you end up with is here's length A, here's length B, and they're sitting on top of length C, but they don't push up enough to open up that angle. So A plus B has to be bigger than C. It turns out it works for the other ones too. B plus C has to be bigger than A, and A plus C has to be bigger than B. That's the triangle inequality. Well, suppose I have a couple of vectors. Suppose I've got a vector v, so here's the magnitude of vector v, and the vector u. And so here's the magnitude of vector u. What can I say about the length of this vector over here? That's the sum of u and v. Well, it should make sense then that the magnitude of u plus the magnitude of v has to be greater than or equal to the magnitude of vector u plus vector v. Here, we're modifying the triangle inequality just a little bit and allowing for the fact that those two things could be equal. If it doesn't form a triangle, it's okay to add the length of two vectors together that are sitting on top of each other, and you'll get the length of their sum. But other than that special case, it has to be that the two vector lengths are greater than the third one. All right, let's look at one other little rule, and that is let's look at these dot products in terms of matrices. So suppose I've got two vectors, and I'm going to write these vectors out as matrices. Vector u is the row vector 1, 3, 5, 7. And vector v is also a row vector 2, 4, 6, 8. What if I take vector v and multiply it by u transpose? Okay, so vector v goes 2, 4, 6, 8. U transpose goes 1, 3, 5, 7. All right, so this one has 1 row and 4 columns. I'm multiplying by something that's got 4 row and 1 column. I'm going to end up with a 1 by 1. What is that 1 by 1? It's going to be 2 times 1 plus 4 times 3 plus 6 times 5 plus 8 times 7. When I add that together, I get the 1 by 1 matrix of 14 and 56. Gives me 70 plus 30 is 100. Okay. You notice that thing is the dot product. And so you can find the dot product by taking those two row vectors, taking the transpose, multiplying them together, and you'll end up with the dot product. Then from there, you can use those types of things if you were in like R2 or R3 to find the angle between the vectors. Right? That's the end of section 1, a whole set of rules about dot products.